Okay, so now we're going to take a look at how we quantify the amount of solute that we have in a solution. And we're going to be looking at a few more concentration units now. So we're going to take a look at quantification of solute in a solution. Okay, and this is what concentration is. We've already seen one concentration unit. We talked a lot about this before, and that is molarity, right? So remember molarity, which is abbreviated big M, moles of solute over liters of the solution, right? So moles of solute over liters of the solution is something that we've seen before, especially when it came to solution stoichiometry and making solutions, etc. We're able to use this to convert between volume and amount in moles using our dimensional analysis. What we're also going to see is something called a mole fraction, which is also something we saw previously back in a couple sections ago, a couple weeks ago. When we were looking at gases, for instance, we know that the mole fraction, right? So again, it's a fraction, it's a unit less, is simply the number of moles of that particular thing. Let's say it's A, for example, divided by the sum of the moles of all of the components in that sample, right? So let's say we had a sample, we have 2 moles of A, okay, 1 mole of B, and 3 moles of C. Well, in the mole fraction, which has this funny looking X, the mole fraction of A, right, would be the number of moles of A. So we have 2A, right, over all the number of moles. So we have 2A plus B plus 3 C's. So this would be now 2 over 2, 3, and 3, 6. So the mole fraction there would be 1/3, right? That's all that the mole fraction is. We're comparing the moles of one component to moles of everything in that solution. The new concentration units that we're going to be looking at now, the first one we're going to take a look at is something called molality, which sounds very similar to molarity, but it's not. There's a second L in there. And it has an abbreviation of small m. So lowercase m is what we use for molality. Okay, and what this is, it's the numerator is the same as in molarity. So we have the moles of the solute. But now what we're going to do is we're going to compare that to not the solution, but the solvent, specifically the mass. And we'll just say, we'll say kilograms of solvent. So now we're comparing the solute to the solvent rather than the solute to the solution. All right. So if we have the moles, the solute, and we have the mass of the solvent, right, we simply divide them as long as they're in the right unit to get the molality. And we say, for example, if you have something like, let's say something like a 1m, 1 lowercase m, sodium sulfate, so Na2SO4 solution. The way that we would read this, we would say 1, instead of molar, we say 1 molal, so Na2SO4. Okay, and what this means, this is the most important thing now, so we have 1 mole of Na2SO4 for every kilogram of the solvent, in this case, kilogram of H2O. Right, that's what this M, 1 molal in this case, would actually mean. And this is the form here that is going to be most useful to us because it allows us to see the relationship between the amount of the solute and the amount of the solvent specifically now in kilograms. All right, the next concentration unit is called the percent concentration, and here we're looking at percent by mass. And we saw percentages back in week 2, maybe week 1, and percent simply means the part over the whole. Okay, so that's what percentage means generally. And then times it by 100 to get a percentage, or to convert it to a percentage. Well, when you have a solution, right, the part is the solute, and then the whole thing is the solution. and then we're going to times it by 100, right? It's the same concept, except now we're looking at mass percent. Okay, so now we're going to be looking at the mass of the solute over the mass of the solution. Okay, that's all that it is. And sometimes you will see the mass percent being represented as M over M percent. Sometimes the mass percent is also called the weight percent, even though they don't mean the exact same thing. They're sometimes used interchangeably. So you'll also see W over W being used to mean the same thing, right? Now, as an extension of the percent by mass, sometimes you will see units such as parts per thousand, parts per million, parts per billion. All that is, it means is the same thing as your percent up here. This, you can think of your percent as meaning parts per 100. I guess what percentage means out of 100. We could also have parts per 1,000. Well, let's go actually move on to the next parts per million, for example. And it will be the same relationship. We're going to be looking at the mass of the solute over the mass of the solution. SOL and the solution. But now for million, parts per million as opposed to parts per 100, we're going to times whatever we get by a million, or 10 to the 6. That's your parts per million, which is often abbreviated as ppm. Okay, we could also, as you can imagine, have ppb, parts per billion. Okay, and that would be the mass of the solute. Again, the relationship is the same over the mass of the solution. And now we're going to times it by a billion, 10 to the 9 to get our ppb. And we usually see those when we're looking at really, 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 really tiny concentrations. You have a really small amount of solute in a fairly large amount of the solution. That's when we invoke those ppm and ppb. And in some cases, parts per trillion, so ppt, sometimes we see that as well. All right, let's take a look at some calculations now, because this is kind of what we're trying to get at here. So if we have select an example. So it says a solution is made by dissolving 770.1 grams of glucose, give you the chemical formula, enough water to make a liter of solution. They tell you the density of the solution is 1.06 grams per mil. I'm just going to highlight these instead. So the density is 1.06. Express the concentration in molality, percent by mass, and parts per million. All right, so we're doing all of those three things in this one problem. So let's see how we can approach this. So the first thing we want to get is molality. And knowing what it means is the first step in figuring this out, right? So we know we just introduced molality. Okay, so molality then would mean the moles of the solute over the kilograms of the solvent. Okay, what's the solute in this case? So we want the moles of the glucose divided by the kilograms of the solvent. So the solvent here is, what do we have? H2O, kilograms of H2O. All right, so let's look at the solute first. So we're given 170.1 grams of glucose. Okay, we want to convert that to moles so we can use it in the example above. So we need to use the molar mass of glucose. You're going to divide by the molar mass. We need to add up 6 carbons, 12 H's, and 6 oxygens, right? So that would be 100 and about 180. So 1 mole, 180.2 grams. grams go away. All right, so we get 0.9440 moles of glucose. All right, so that's the numerator here that we just found. Now we need the kilograms of H2O. Now we're not given any information about water except to say that we have enough water to make a liter of the solution, and they give us the density of that solution. All right, so with the solution now, what we can do is use a density and convert the liter into grams. Okay, so we have the density of the solution, 1.062 grams per mil. Okay, and we also have 1 liter of solution. So we have volume, we have density, we can find the mass of that solution. So I have my 1.062 grams per mil. I'm going to multiply it by a liter, which is 1,000 mils. Okay, so that's going to give me 1,062 grams of the solution. Okay, that's the solution now. I know how much glucose I have in that solution, 170.1. So if I subtract the mass of the glucose, which is the solute, then whatever mass I get would be the mass of the solvent. All right, so if I subtract those two, I get 892 grams of water, which is the solvent. And then we want kilograms, so we divide that by 1,000. So that's going to be, so we get 0.892 kilograms of our solvent. Okay, so we have the denominator, we have the numerator. We're going to stick this into our equation now. So we have, what was it, 0.9440 moles of glucose divided by 0.892 kilograms of glucose. And then we evaluate that, we'll get our concentration in molal, which ends up being 1.06. And then lowercase m molal would be our unit. So that tells me I have 1.06 moles of glucose for every kilogram of water. All right, the second one, percent by mass. Okay, so percent by mass here would be mass of the solute, which is the glucose, over the mass of the solution, right? Part over the whole, and then times 100. So we know what the mass of the glucose is. It's 170.1 grams. Now we've already found the mass of the solution from this, what we did before. So we had 1,062 grams of the solution. So we just divide those, times it by 100. Grams go away. We get our percentage as our unit. So 170.1 divided by 1062 would give 16.02%. By mass of glucose. So what that also means, okay, so just to make it easier to interpret, if you're given a percent by mass, what this also means is that if you had 100 grams of the solution, guess how much of it would be the solute? 16.02 grams of the solute, right? That's a way to interpret these percentages by mass that you're provided with. You just make it out of 100 because that's what percentage means, and then you just put that number in the numerator. Okay, and then the third thing here we need to calculate is the the parts per million. Okay, so parts per million, very similar to the percentage by mass. So ppm, parts per million, would be the same initial part of this here, mass of the glucose, the solute, over the mass of the solution. Okay, and then for parts per million, we're going to times that by a million, 10 to the 6th. Okay, so we have again the 170.1 grams over the 1062 grams. Grams going to cancel, times that by a million. Okay, and then that is going to give us a much larger value. We get 1.602 times 10 to the 5. ppm of glucose. Fairly large concentration, especially when you use that particular unit of concentration. So a couple of things to note here. We've seen some new concentration units. When do you use one concentration unit versus another one? Well, it kind of depends on what is it that you're trying to do. Okay, so for example, we've done lots of titrations, or we've at least done one titration. We've looked at other examples of titrations. In those cases, we would probably use molarity because that's the most applicable one to use. When we're dealing with gases and vapor pressure, mole fraction would probably be a better one to use. And in other cases, we can use molality and percent by mass, where temperatures and whatnot are not really that important. Okay, let's take a look at another example where we're going to go between different, to calculate different concentration units. So it says rubbing alcohol is a mixture of isopropyl alcohol and water that is 70% isopropyl alcohol by mass. It gives you the density of the rubbing alcohol solution. We want to express this in molarity and molality. So first thing, let's look at the molarity first. So again, molarity, okay, this is moles of solute over liters of the solution. Okay, so in this example, we're given 70% by mass of isopropyl alcohol, right? So we're given here 70% by mass. And we'll abbreviate isopropyl alcohol as IPA. Then rubbing alcohol as RA. Okay, so 70% by mass of isopropyl alcohol in the rubbing alcohol solution. So what does this mean? 70% by mass of IPA. That's the most important thing. And if you're not given an actual amount of this thing, the best thing to do is to assume you have 100 grams of it. That will make the calculation a lot easier of the solution in this case. So the one that would mean then would mean that 70 grams, we would have 70 grams of IPA, isopropyl alcohol, in 100 grams of the rubbing alcohol solution, right? That's what 70% means. So in order to now determine the molarity, I need the moles of the solute. Well, here I have the grams of the solute. I need to convert that to moles of IPA, isopropyl alcohol. So I'm going to use the molar mass, so 70 grams of IPA. And then for every 1 mole of isopropyl alcohol, we're given the formula, calculate the molar mass, which it says down here is 60.09 grams of IPA. Okay, that goes away. And that is going to give us 1.2 moles of isopropyl alcohol. So that's our numerator up here. Now we need the liters of the solution, right? So in our percent by mass interpretation, right, we have mass of the solute over mass of the solution, right? So the 100 grams here is the grams of the solution. So we have 100 grams of the rubbing alcohol solution. Can we convert that to liters? Well, the answer is yes, because we're given the density of that. So we can use that density. It says for every 1 milliliter of that solution, we have 0.79 grams of rubbing alcohol. So that can go. I just took my density and I flipped it to make it a conversion factor. That would be useful to me. So 100 divided by 0.79 gives, what is that, 0.1 or 127 mils. We need that in liters, right? We have liters in our denominator. So we divide by 1,000, that would be 0.127 liters of the rubbing alcohol solution. So we have both of those things to calculate molarity. So big M molarity will be the moles. So we have 1.2 moles divided by the liters, 0.127 liters, and that would give us, let's see here, we would get 9.2 molar isopropyl alcohol. The second part of this is to now determine the molality. Okay, so let's take a look at molality on the other side. Okay, and again, molality, lowercase m, is the moles of solute, which we already found, divided now by the kilograms of the solvent. Okay, so moles of solute we calculated down here. What was it? No, it was up here, 1.2 moles. Okay, and now we want the kilograms of the solvent. So we know that we assumed, since we assumed 100 grams of the solution. Remember, the solution is the sum of the solute and the solvent. Well, the solute there was 70 grams because it was a 70% solution. So 70 plus something gives me 100. That would mean the solvent then, which is our H2O, would be 30 grams of the solvent. We need this in kilograms in order to calculate molality. So we divide that by 1,000. 1, 2, 3, that'd be 0.030 kilograms. That's going to go in here. So our molality M would be equal to 1.2 moles divided by 0.030 kilograms. All right, and that is going to give, let's see, 1.2 divided by 0.03. Oops. Would give, or within a rounding error, that would give 39 molal. For the concentration in molality. So when you are doing these problems, okay, the first step is to figure out, well, what am I being asked to calculate? And then if it's molarity, right, expressing it in the correct units, not just moles, but moles of what? Moles of solute over liters. Liters of what? Liters of solution. Similarly, molality, moles of solute over kilograms of the solvent. If you're, especially for the percentages, if you're not given an actual amount of something, just assume that you have 100 grams of that thing. It would make your calculation a lot easier. But you could just as easily assume any other amount that you wanted to. You could assume a kilogram, you could assume an ounce, you could assume a ton, doesn't matter. But it makes sense to assume 100 grams because percentages are out of 100.